This lesson is going to be looking at catalysts and chemical reaction. Learning target is to be able to classify chemical reactions based on energy changes. And we want to be able to explain um, how chemical reactions can speed up and know the reasons why these can speed up. And then we'll take that and we'll look at how catalysts can affect the energy that's needed to start a chemical reaction. So we're looking at chemical reactions and we're trying to figure out what's going on in a chemical reaction. We've learned some things about this, but there's a little bit more to the story. So we know that we're having reactants that we're starting out with. We know that it's going to take some energy going in to break the bonds of those compounds that we're starting with that are reactants. We know that some sort of a chemical reaction is happening. Something's happening here. These atoms are going to rearrange, and then we have some energy that is given off once we form new bonds in our products when those atoms rearrange. We know that we're not gaining or losing any atoms in this reaction. We know we have this exact same amount on both our reactant and our product side, but somehow they rearrange those atoms and form new products, giving off some energy. We also know that if I take more energy in than I give off, that's an endothermic reaction or reactions absorbing energy. If I give off more energy than I take in, my product side, let's say I was going to draw a really big arrow here. If I'm giving off more energy than I take in, the surroundings of my reaction are going to heat up. It's going to be an exothermic reaction because energy is exiting more than it's entering. But what's really going on in a chemical reaction is that molecules are colliding. This is why this is happening, is we have our compounds in our reactants that are colliding with one another. And there's a few things that have to happen in order for a reaction to take place. Number one, the molecules have to actually collide. They have to come close enough to run into each other that there would be enough of a collision, enough energy in the collision where the bonds would break apart and then they'd be able to reform new um, compounds. They have to have enough energy in order to break those bonds. So this energy that's going in has to come from somewhere, and it's going to come from the kinetic energy of those molecules as they run into each other. And so they have to have enough energy in order for a reaction to happen. And they also have to be the right match. If I've got two compounds that one are probably not likely to run into each other or not likely to react with each other, then there's not going to be a reaction that takes place. So we have to have the right ones that are going to run into each other. So when we think about how we could speed up a chemical reaction, we can figure it out based off of these things that I just underlined right here, these three conditions. So when we're looking at how could we speed up a chemical reaction, one way that we could do it is to raise the temperature of wherever the reaction's happening, whether that's in a liquid, whether it's in a gas, um, is to raise the temperature. And we can go back to what we know about the temperature in matter, and that the temperature is a direct relationship. It's actually the temperature is telling us how much kinetic energy the molecules in whatever we're measuring the temperature of have. And remember, the kinetic energy is how fast they're moving. And so if we raise the temperature, we're actually increasing the speed and the kinetic energy of these molecules. And it doesn't just help us that they have more energy because they're moving faster, and so they're more likely to react if they do collide, but I mean, you can envision some molecules moving around pretty quickly in a little closed container. If they're moving faster, they're more likely to run into each other. That just makes sense. And so raising the temperature speeds up a chemical reaction. We can also increase the concentration of our chemicals. And that would basically just mean how many molecules we have in either a liquid or in the air or in a gas or anything. How many molecules are in this space that the reaction's happening? And again, if we have more molecules in this space, we increase the concentration. There's going to be more collisions, and it's going to be more likely that they're going to run into a molecule that is the right match. If we have more molecules in whatever this thing is, this would be as if like I don't know, I dump in just a little scoop of a chemical in here, as opposed to dumping in a really big scoop. If I dump in a lot of whatever chemicals I'm using, obviously there's going to be more likely that a reaction is going to happen. It's going to happen faster. So if I increase the concentration of my chemicals, the speed of my reaction is going to go up. That makes sense. Another way that we can do it, and I'm just going to write stir for this. Um, if I stir whatever either liquid or a gas or wherever this reaction is happening, if I stir that, these molecules are more likely to collide with each other. They're going to be all stirred up. They're going to be more likely to run into each other, and they're going to be moving around in a way that's going to bring them more likely to run into a molecule that has a match with it. We know that if I stir something up, it's going to dissolve faster. The same process happens in a chemical reaction. Those molecules are more likely to find a match that a reaction could happen with. The reaction is going to take place faster. Another way that this could be is if we like break up chunks in our chemical reaction. If I have maybe like a sugar cube that I'm dumping into some water, and that's going to dissolve slower than if I have just a bunch of little tiny sugar crystals if I dumped in like granulated sugar. And for this example, it's because there's more surface area here. There's more likelihood that these molecules are going to run into each other than if I have this little sugar cube right here. If I have this sugar cube here, there's a lot of sugar in the inside of this cube that's not going to come in contact with the water when it's trying to dissolve. You can think about it the same way as a chemical reaction. If I have a bunch of chunks of chemicals that I'm putting in here and waiting for them to react, well, the stuff on the inside isn't going to react before the stuff on the outside does. And so by breaking it up, I'm giving more of those molecules, the compounds, a chance to react. So those three things, raising the temperature, raising the concentration of our chemicals, and stirring or breaking up whatever it is that we're trying to react, are all going to speed up a chemical reaction. And another thing that can speed up a chemical reaction is called a catalyst. And so a catalyst is something that participates in the chemical reaction but is not used up. That's something that you should write down. A catalyst is something that participates in the chemical reaction but is not used up. It's something that we can add to our reaction. It's going to make it go faster, but it's always going to be there. It's not going to be used up in the process like a reactant where it's going to be changed into a product. It's going to stay the same. And so if we were going to draw chemical formula, reactants to products. Sorry, heat energy, I'm going to get rid of you. Sometimes we'll see something that says cat right above this arrow. And the purpose of this is to say that yes, there is a catalyst acting in this reaction, but no, it's not changed in the reaction. It's always going to be there. And even when the reaction's done and all of our reactants are turned into products, there's still going to be a catalyst there. So it's something that we add to the chemical reaction that does not get used up in there, but it does speed it up. Here, we'll get rid of our writing here. And the way that it affects a chemical reaction is that it reduces the activation energy of the reaction. So you should write that down as well as how it affects a chemical reaction. What a catalyst does is essentially makes it more likely that these molecules are going to collide in a way that's going to start a reaction. It's going to cause them to need less energy when they collide with each other. There's a bunch of different ways that this could happen, and we're not really going to get into that part of it. But essentially, it's going to take this hump that we know needs to happen for the chemical bonds to break in our reactants, and it's going to make it smaller. So we don't have to quite put in as much energy here. And our curve will look something like this. And so now our activation energy is much smaller. And again, if we're looking at molecules that need to have a certain amount of energy in order for a reaction to take place, and now we just reduced the amount of energy they need to have for a reaction to take place, well, more molecules are going to be able to react then, and thus our reaction is going to happen faster. And so that is how a catalyst will increase the rate of a chemical reaction. They're going to speed it up because they reduce the activation energy. So if we're looking at our energy graphs, just to review this again, we want to understand how chemical reactions work in terms of energy here. And so our endothermic reaction, again, is a reaction that starts off with reactants with lower energy than our products. There's a certain amount of activation energy it takes to get that reaction started. And remember that a catalyst would reduce that amount of energy that it would take to get this reaction started. Okay. And then this energy down here, our energy that's absorbed, this is the difference in energy between our reactants and our products. Since our products have more energy than our reactants, that means that we put energy into this reaction that we didn't quite get back. Again, we did put in some energy to break those bonds, and we didn't get quite as much out in this one. So this is an endothermic reaction. And remember, this one would feel cold to the surroundings because it's taking in energy. Our exothermic reaction over here, again, has our activation energy, and our catalyst would, again, reduce that activation energy that's going through. Our products would have less energy than our reactants. And this would be an exothermic reaction because it's going to be giving off energy. This difference right here from what our reactants started with for energy and our products now have, there's extra energy here. And so we're going to be giving this off, and that's why these are going to feel hot in their surroundings because the reaction, the compounds that are rearranging into new compounds are going to be giving off energy. And so I hope that this helps to understand how the energy works in a chemical reaction, how a catalyst can affect that.